If you were to stand on the surface of the moon and look back across the dark, silent void of space, you would see a sight that stands in stark defiance of the rest of the solar system. You would see a brilliant sapphire sphere, wrapped in swirling white clouds, gleaming against the endless black backdrop. It looks peaceful, it looks inviting, it looks like a jewel. But to a cosmologist, this blue marble is more than just beautiful. It is a problem. It is a profound, deeply perplexing paradox. By all the established laws of physics and planetary formation, that water simply shouldn't be there. We live on a planet that is 70% covered in liquid ocean, yet we orbit a star that is a blinding nuclear furnace. We exist in a zone of the solar system where extreme thermal radiation should have boiled every single drop of moisture away billions of years ago. The Earth should be a dry, scorched, desolate rock, as barren as Mercury or as dusty and lifeless as Mars. But instead, we are drowning in oceans. This water is the defining feature of our world, the cradle of our biology, and the universal solvent of our very existence. Yet its true origin remains one of the deepest, most fiercely contested mysteries in modern science. Did it fall from the sky in a relentless, chaotic rain of icy comets? Did it bleed from the primordial rocks themselves during the planet's infancy? Or is it a ghost, a remnant from an ancient time before the Earth even condensed into a solid sphere? Tonight, we trace the epic, multi-billion-year origin of the oceans. We will go back to the Age of Fire, to the era of the great atmospheric rains, and uncover the secret history of the water resting in your glass. So, before you get comfortable and let the weight of the day drift away, take a quick moment to like the video and subscribe to Midnight Sleep Documentary, but only if you genuinely enjoy what I do here. And please let me know in the comments where you're tuning in from and what time it is for you right now. It's always fascinating to see who is joining us from around the world. Now, dim the lights, turn on a fan for that soft, rhythmic background hum, and let's ease into tonight's journey together. To truly understand why our oceans are such a monumental scientific mystery, we must first look at our immediate cosmic neighbors. The inner solar system is an unforgiving neighborhood of rock, metal, and relentless thermal radiation. Mercury, the closest planet to the Sun, is a blistered, airless world of dense iron and stone baked by relentless solar radiation. Venus, often called our twin in size and composition, is a suffocating hellscape of crushing atmospheric pressure and runaway greenhouse heat, where any primordial water that might have once existed was violently boiled off into space eons ago. Mars, the red planet, is a frozen, desiccated desert, a world where water exists almost entirely as ice, trapped in the polar caps or buried deep within the soil, a pale fossil of a wetter past. And then there is Earth. We are the grand anomaly. We are the only world in the known cosmos where water exists simultaneously in all three physical states, as solid ice, as gaseous vapor, and crucially, as liquid. We are a flourishing water world, sitting squarely in a region of space that is fiercely hostile to volatile liquid compounds. The sheer physical volume of this liquid is staggering. There are over 1.3 billion cubic kilometers of water sitting on our planet's surface. It fills giant oceanic basins 5 miles deep. It carves towering rock canyons. It saturates our atmosphere, and it flows through the veins and cells of every living organism on Earth. This vast abundance directly defies the standard accretion models of how terrestrial planets are built. In the violent, hot, swirling accretion disk of cosmic dust and gas, from which the young solar system condensed, the region close to the newborn sun was simply too hot for water to condense into liquid or ice. Volatile compounds like H2O should have been vaporized and forcefully blown outward to the frigid edges of the system by the fierce early solar wind. The proto-Earth formed directly inside this hot, dry zone. It was constructed from dry, rocky materials in a dry region under a blazing young star. Therefore, when you gaze out across the vast expanse of the Pacific Ocean, you are looking at something that theoretically should not exist on our world. It is an alien substance that has somehow found a permanent home where it logically doesn't belong. To figure out how it got here, we must journey back to the fundamental physics of the early solar system and look closely at the invisible boundary that divides our planetary neighborhood in two. Astronomers have mapped this invisible boundary, a critical thermal border known in astrophysics as the frost line or the snow line. The physics of the snow line work on the very same principles as a roaring campfire on a bitterly cold winter night. If you stand too close to the fire, it is far too hot for frost or snow to linger. Any water turns instantly to invisible steam. But if you walk far enough away into the dark, cold periphery, you cross a precise physical threshold where the thermal radiation drops low enough for water vapor to condense and freeze into solid ice. In the early solar nebula, 4.5 billion years ago, this thermal boundary was located roughly between the present-day orbits of Mars and Jupiter. Everything inside this line, Mercury, Venus, Earth, and Mars, formed inside the hot, volatile, depleted dry zone. Here, the intense heat radiating from the young T-Tauri sun completely vaporized volatile elements. The microscopic dust grains that clumped together via gravitational attraction to build our rocky world were metallic and silicate-based, stripped bare of their moisture. But beyond the frost line, out in the frigid, shadowed expanses where the gas giants dwell, water ice was as abundant as rock. Out there, H2O condensed into massive, rock-hard ice crystals, forming vast, orbiting reservoirs of icy planetesimals, comets, and frozen moons. According to the classical laws of planetary formation, the Earth sits squarely on the wrong side of the fence. We are physically built from the dry, baked dust of the inner solar system, yet our surface is drowned in the volatile ice of the outer system. How this massive volume of volatile material bridged the thermal gap between the outer frozen depths and the hot inner terrestrial zone is a grand puzzle. The early solar nebula was a chaotic place filled with swirling gas currents, gravitational resonances, and millions of protoplanetary fragments colliding at high velocities. As dust grains collided, they formed pebbles, then boulders, and eventually planetesimals tens of kilometers wide. As these bodies grew, their gravitational pull intensified, sweeping up more material in their orbital paths. But because this entire process was occurring inside the frost line, every grain of sand, every chunk of basalt, and every iron-nickel fragment that coalesced to build the proto-Earth was fundamentally dry. The primordial dust lacked hydrated minerals. The local environment was simply too hot for water molecules to cling to the surface of the accumulating particles. In classical accretion physics, the early Earth should have emerged as a completely dry, dense sphere of silicate rock and metallic iron, devoid of an ocean, devoid of an atmosphere, and devoid of the essential liquid ingredients that make life possible. Yet today, we look around at a world defined by its oceans. The contradiction between where our planet formed and what our planet is made of is the core mystery that scientists have spent centuries trying to solve. Was our world truly born dry, only to be soaked later by external space rocks? Or was water secretly embedded inside the rock from the very beginning, waiting for the right thermal conditions to escape to the surface? To understand this deep cosmological paradox, we must realize that the early solar system was not the calm, orderly clockwork mechanism we see today. It was an unhinged cosmic demolition derby, a place of extreme instability where giant protoplanetary engines drifted across vast orbital distances, tearing apart protoplanets and flinging frozen debris across trillions of miles of empty space. If the inner nebula was an arid desert, then any liquid that ended up on our world represents a massive transportation event across the solar system. Either huge quantities of ice migrated across the frost line, crossing millions of kilometers of thermal fire to deliver their icy cargo directly into Earth's gravity well, Or, our current understanding of the temperature profile of the primordial accretion disk is completely wrong. Scientists have calculated the mass of our oceans and determined that liquid water accounts for roughly 0.02% of the Earth's total mass. While that percentage sounds small, in absolute terms, it represents an astronomical amount of material. 1.4 billion trillion kilograms of pure liquid H2O resting right on the outer crust. If you were to spread that water evenly across a perfectly smooth, spherically uniform Earth, without continents or trenches, it would form a global ocean over 2.5 kilometers deep, everywhere on the surface. Where could such an immense volume of volatile substance come from on a planet that was forged inside a thermal furnace? Why did Earth end up with this vast liquid biosphere while our immediate planetary neighbors, Venus and Mars, ended up as desiccated, lifeless rock piles? Was Earth merely lucky in the cosmic lottery, hitting a rare mathematical sweet spot of planetary distance, magnetic protection, and gravitational mass? Or is the presence of liquid water on a terrestrial world an inevitable consequence of how planets cool, process rock, and evolve over geological epochs? When we analyze the chemical composition of our atmosphere today, we find only tiny traces of primordial hydrogen and helium, the gases that dominated the early solar system. This tells us that whatever primordial atmosphere Earth had when it first formed was completely blown away into space. The atmosphere we breathe now and the oceans that cover our crust are secondary features. They arrived later, or they emerged from deep within the belly of the planet after the initial storm of creation had subsided. To uncover how this secondary layer of water took over our world, we must turn back the clock to the very beginning of planetary history. We must examine the terrifying, violent era of planetary accretion, a time when our world was not a serene blue oasis floating in the dark, but a scorching, glowing fireball of liquid rock spinning wildly under a hostile orange sky. The birth of our planet was not a gentle, gradual accumulation of peaceful cosmic dust. It was a violent, chaotic demolition derby, occurring on a planetary scale. 4.5 billion years ago, the proto-Earth grew through the process of runaway gravitational accretion. Countless planetesimals, protoplanetary fragments, and massive rocky asteroids collided with one another, their mutual gravitational pull continuously dragging them together into a growing, turbulent sphere. Each one of these cosmic collisions released a staggering amount of kinetic energy. Upon impact, that kinetic energy was instantly converted into pure thermal heat, flash melting the colliding bodies and baking the growing protoplanet. The young Earth was not merely warm or geologically active, it was completely molten. It was a world constructed entirely of liquid stone, glowing white-hot against the cold, dark vacuum of space. In this terrifying forge of planetary creation, volatile elements like water faced an immediate existential crisis. Even if trace amounts of moisture had been trapped inside the crystal lattices of the colliding primordial rocks, the violent, unrelenting heat of continuous impacts would have instantly boiled that water away. Hydrated minerals would have broken down under the extreme thermal pressure, releasing their bound water as superheated steam. This liberated steam would have risen rapidly through the buoyant, churning surface to form a thick, primordial atmospheric envelope. But this early steam atmosphere had no protection. The newborn sun was a young, highly unstable T-Tauri star, unleashing violent bursts of intense ultraviolet radiation and violent solar storms far more energetic than anything our star produces today. This fierce solar wind continuously swept past the defenseless protoplanet, scouring its outer envelope and blasting light volatile molecules like H2O directly out into the interstellar vacuum. The classical accretion model paints a clear and grim picture of the infant Earth. Our world emerged as a bone-dry, sterile rock, a glowing ball of churning liquid magma orbiting inside a cloud of cosmic dust. It possessed an immense core of dense molten iron and nickel, overlaid by a thick mantle of churning silicate rock, but it lacked the crucial volatile ingredients required to foster life. It was a world devoid of oceans, lakes, or atmosphere, a scorched sphere without a single drop of blue. Let us journey back to that primordial age, the Hadean Eon. Named appropriately after Hades, the ancient Greek underworld, the Hadean Eon represents the most hostile chapter in the geological biography of our planet. If you were to stand on the surface of the Earth 4.5 billion years ago, you would not recognize a single feature of the world we inhabit today. There were no stable continents, there was no lush greenery, there were no deep, rolling blue seas. Instead, the entire surface was a churning, glowing, turbulent ocean of liquid stone, a global field of incandescent magma radiating searing heat into space. The sky above this magma sea was not the clear, comforting blue we know today, but a hazy, toxic, suffocating canopy of dark orange and deep crimson. It was choked with dense carbon dioxide, atmospheric nitrogen, heavy sulfur compounds, and vaporized rock particles. The atmospheric pressure resting on the liquid surface would have been crushing, many times greater than the modern sea-level atmosphere. In this hellish, high-temperature landscape, liquid water was a physical impossibility. Any hypothetical molecule of liquid H2O that somehow made contact with the glowing magma ocean would have instantly flashed into superheated steam, expanding explosively and floating upward into the extreme reaches of the atmosphere, where solar radiation would strip its hydrogen atoms away forever. This was the absolute zero point of our planet's hydrology, a scorched world defined entirely by the absolute absence of the liquid that now defines it. And yet, as we look back at this terrifying ball of fire, we know that an extraordinary metamorphosis was on the horizon. Somehow, against all physical odds, this glowing sphere of melted rock had to cool down, stabilize, and transform its dry, baked surface into a wet, thriving cradle for life. The transition from the extreme fire of the Hadean hellscape to the refreshing waters of a global ocean represents the single greatest planetary transformation in the history of our solar system. Just as the young Earth was slowly beginning to radiate its initial heat into space, and just as a paper-thin, fragile skin of dark basalt crust was starting to form over the churning magma ocean, the solar system delivered a catastrophic cosmic blow that completely reset the planetary clock. This colossal event is known to modern astrophysics as the giant impact hypothesis. Evidence suggests that 4.5 billion years ago, the proto-Earth was not orbiting the Sun alone. It was being actively stalked by another massive protoplanetary body, a Mars-sized world that scientists have named Theia. Theia was orbiting in an unstable gravitational relationship with Earth, drifting closer with every orbital revolution, until a devastating collision became mathematically inevitable. Theia slammed into the proto-Earth at an oblique angle with a violent force that completely defies human imagination. It was not merely a large impact, it was a full planetary merger. The kinetic shockwave generated by the impact was so massive that it completely liquefied both planetary bodies, melting their mantles and turning the combined mass back into a churning, white-hot sphere of superheated rock and vaporized metal. The violent impact blasted trillions of tons of incandescent molten debris into orbit around the Earth, forming a massive ring of fire that would gradually coalesce over thousands of years to form our moon. But for the history of Earth's water, the giant impact was a complete, absolute sterilization event. The extreme temperatures generated by the impact reached thousands of degrees Celsius, far exceeding the vaporization thresholds of every volatile compound in existence. If any early water molecules had managed to stay trapped within damp rocks or shallow early steam reservoirs prior to the collision, the giant impact obliterated them completely. The immense heat broke apart chemical bonds, vaporizing all volatile gases and driving them outward into the orbital debris field. Massive amounts of light hydrogen were lost to the vacuum of space forever, leaving the remaining Earth-Moon system utterly parched. The Earth was left spinning rapidly on its tilted axis, wobbling through space as a freshly melted, completely sterile sphere of glowing lava. The giant impact had functioned as a cosmic reset button, guaranteeing that our planet would have to start its geological journey from absolute zero, a bone-dry, scorching baseline, stripped of all its original surface volatiles. Following the unimaginable violence of the Theia collision, a profound, eerie silence fell across the inner solar system. The cloud of orbiting impact debris gradually settled, sweeping together to build the Moon, which orbited much closer to the Earth than it does today, looming impossibly large in the dark, silent night sky. On Earth, the long, excruciatingly slow process of cooling began once again. The global magma ocean, which had been churning and glowing white-hot for thousands of kilometers beneath the atmosphere, began to lose its intense energy. Thermal radiation escaped continuously into the dark void of space, causing the extreme temperatures of the surface to drop. The dazzling white-hot lava cooled to a deep, incandescent red, and slowly, a solid outer skin began to form on top of the liquid rock. This skin was the Earth's very first crust. It was a jagged, unstable, razor-sharp expanse of jet-black basalt and glassy obsidian. It was brittle and fragile, constantly breaking apart under the pressure of the boiling magma beneath it, sinking back into the glowing depths, only to freeze into solid rock once more. Imagine a terrifying, monochromatic landscape of dark volcanic glass cracking open under a faint, distant sun. There was no sound of wind or rain, for the atmosphere was still extremely thin and devoid of weather systems. There was no sound of crashing ocean waves. The only sounds echoing across the dark, silent world were the loud, metallic cracks of cooling rock splitting open and the deep, low, seismic rumbles echoing from the heavy mantle beneath. It was a completely dry, desolate world of black stone. The stage was set, and the planetary vessel had been formed. The basin was ready, but it was entirely empty. The Earth was a completely dry, parched desert floating through the cold darkness of space, holding no liquid water of its own and waiting for a massive delivery of volatiles from an external source. If Earth was ever to transform into a living water world, that water would have to travel across millions of miles of space from the cold, icy outer reaches of the solar system. As thermal dissipation continued, the outer mantle began to solidify down to deeper levels. The convective motion of liquid stone slowed down, allowing the brittle basalt surface to thicken from a thin film into a continuous geological shield. Yet, beneath this dark shield, intense thermal energy remained trapped, building up immense pressure within the planet's core and lower mantle. Without an insulating liquid ocean or a protective atmospheric blanket, the surface temperatures were dictated entirely by the balance between internal radioactive heat loss and the direct radiation of the young sun. The planet existed in a suspended, sterile state, a giant spherical vault of dark silicate basalt floating in vacuum, completely ready to receive the volatile cargo that the cosmos was about to unleash. Every volcanic fissure that cracked open on this early crust released residual gases trapped in the upper mantle. But these initial outgassings were dominated by heavy silicates, sulfur compounds, carbon monoxide, and raw carbon dioxide. Hydrogen was extremely scarce, having been blown into the void during the impact phase. The planet was physically incapable of manufacturing water from scratch on its surface. The necessary hydrogen building blocks were missing from the immediate planetary reservoir. Thus, the early Earth orbited the Sun as a silent, black monument to accretionary physics, a giant, dry rock waiting in the dark void for an external mechanism to deliver the life-giving liquid that would define its destiny. That delivery mechanism was already taking shape far out in the frozen depths of the outer solar system, where giant ice worlds were shifting their orbits and preparing to fling millions of icy bodies directly into the inner terrestrial zone. After the violence of the giant impact and the initial cooling of the basaltic crust, the young planet was a bone-dry, sterile vessel waiting for liquid. And about 3.9 billion years ago, the grand supply run finally arrived. The solar system was not the stable, clockwork mechanism we observe today. The giant gas worlds, Jupiter and Saturn, were undergoing a profound gravitational migration, shifting their orbits in a complex celestial dance that threw the surrounding primordial debris into complete orbital chaos. Their immense gravitational fields acted like giant cosmic slingshots, violently disrupting the stable orbits of millions of icy planetesimals, asteroids, and comets residing in the cold outer reaches of the solar nebula. These icy bodies were hurled inward toward the Sun, directly crossing the path of the young Earth. This turbulent geological epoch is known as the Late Heavy Bombardment. For tens of millions of years, the sky literally fell. The Earth was relentlessly hammered by a continuous rain of cosmic debris. These were not minor shooting stars or tiny meteorites. They were mountain-sized chunks of rock, metal, and volatile ice slamming into the black crust with the kinetic energy of vast nuclear arsenals. Looking up from the cooling surface, the night sky would have been a terrifying kaleidoscope of blinding streaks, atmospheric entry fireballs, and massive impacts. Yet, this relentless catastrophe was not an ending. It was a grand cosmic delivery service. These impactors were the carriers, the cosmic freighters, loaded with the exact volatile elements Earth completely lacked. They were bringing organic compounds, frozen atmospheric gases, and most importantly, trillions of tons of water ice that would eventually turn the black, glassy planet into a brilliant blue world. When scientists first began searching for the specific delivery mechanism of Earth's water, their eyes turned naturally toward the outermost edge of the solar system. Far beyond the orbit of Neptune lay the comets. Comets are the dirty snowballs of the cosmos. Ancient, pristine remnants frozen in time since the dawn of the solar system, composed largely of frozen carbon dioxide, methane, dust, and vast quantities of water ice. They seem to be the perfect candidate for the origin of the oceans. When a comet falls toward the inner solar system, solar heat causes its ice to sublimate, releasing a magnificent glowing tail of water vapor millions of miles long. Visible, physical proof of the massive water payload locked within its core. For decades, the dominant scientific theory held that comets were the primary architects of our oceans. The math seemed elegant and straightforward. During the late heavy bombardment, millions of these icy wanderers would have crashed into the Earth. Each impact would deliver a massive payload of water ice, which would instantly flash into superheated steam upon entry, gradually building up a massive steam atmosphere around the cooling world. It was a poetic notion, the idea that every drop of liquid in our rivers and seas was once frozen ice, floating in the deepest, coldest abysses of the outer galaxy. It suggested that Earth was simply an empty bucket filled up over time by an external cosmic hose. However, empirical science requires precise isotopic evidence, not merely elegant hypotheses. To definitively prove that comets built our oceans, astrochemists needed to analyze the chemical signature of cometary water and compare it directly to the chemical fingerprint of the water covering our planet today. Water is not simply H2O in every instance. In nature, a small fraction of hydrogen atoms carry an extra neutron in their nucleus, transforming normal hydrogen into deuterium or heavy hydrogen. The relative ratio of standard hydrogen to heavy hydrogen in a water sample acts as an unalterable isotopic fingerprint. This deuterium to hydrogen ratio reveals the precise temperature, pressure, and cosmic conditions under which the water was originally forged. In 2014, the European Space Agency's Rosetta mission achieved a monumental triumph of spatial navigation. After a 10-year chase across billions of miles of empty space, the Rosetta spacecraft caught up with Comet 67P/Churyumov-Gerasimenko. It deployed the Philae lander directly onto the comet's icy, jagged surface to physically sample the outgassing water vapor and measure its exact isotopic composition. The results, returned by Rosetta, sent shockwaves through the scientific community. The water vapor spewing from Comet 67P was vastly different from Earth's water. It possessed a deuterium to hydrogen ratio more than 3 times higher than the ratio found in Earth's oceans today. It was an unmistakable chemical mismatch. If Earth's oceans had been primarily delivered by comets like 67P, the chemical fingerprint of our oceans would be radically heavier than what we observe. This crucial measurement effectively ruled out Oort cloud and Kuiper belt comets as the primary source of Earth's water. The romantic theory of melted comets collapsed under the weight of isotopic data. While comets may have added a faint dusting of water to the upper atmosphere, they were not responsible for filling the vast oceanic basins. With the comet hypothesis largely dismantled by isotopic evidence, astrochemists turned their attention away from the distant, icy comets and focused on closer, rockier space bodies, the asteroids. Specifically, researchers began studying a rare, ancient class of meteorites known as carbonaceous chondrites. To the untrained eye, these space rocks appear as dull, dark gray, unimpressive stones. They do not display glowing vapor tails, nor do they shimmer with visible ice. Yet, appearances in planetary science can be deeply deceiving. Carbonaceous chondrites are essentially microscopic cosmic sponges. Their underlying mineral matrix is loaded with hydrous clay minerals, silicates that have water molecules chemically bound tight inside their crystal lattice structures. Some of these meteorites are composed of up to 20% water by total weight. These carbonaceous asteroids formed much closer to Earth than comets, within the outer reaches of the main asteroid belt. This region was cool enough for hydrous clay minerals to form and remain stable, but warm enough to prevent the accumulation of pure, deuterium-rich water ice. During the violent migrations of the giant planets, trillions of these carbonaceous bodies were flung inward, raining down continuously onto the early Earth. They did not bring water as liquid pools or surface ice sheets, but as microscopic dampness securely locked within stone. As these meteorites slammed into the Earth at hypersonic speeds, the extreme kinetic energy of the impacts shattered the crystalline structures of the clay minerals, liberating the bound moisture and releasing it instantly into the growing atmosphere as hot steam. This process was not a sudden, dramatic deluge, but an excruciatingly slow, grinding accumulation occurring over tens of millions of years. Impact by impact, meteor by meteor, stone by stone, the raw material for our oceans was delivered in the form of hydrated space dust. Science calls this model the late veneer theory. The late veneer theory proposes that the vibrant blue covering our world is essentially a late chemical addition, a thin, wet layer of hydrated material delivered by rocky asteroidal freighters that struck the planet just after its primary core and mantle formation had completed. Analyses of carbonaceous chondrites recovered on Earth show that their deuterium to hydrogen ratio matches the exact isotopic signature of Earth's modern seawater. For decades, this scenario satisfied the scientific community. It provided a clear, verifiable mechanism that reconciled the dry formation of the inner solar system with the massive presence of water on Earth's surface. The Earth was viewed as an empty, baked clay bowl that was slowly filled up by a relentless rain of damp asteroids during the chaotic aftermath of planetary formation. Yet, even as the late veneer theory gained widespread acceptance, new geochemical anomalies began to emerge from deep planetary modeling. Calculations revealed that to deliver the sheer volume of water present on Earth today, the required mass of incoming carbonaceous asteroids during the late heavy bombardment would have left behind unusually high concentrations of precious metals like platinum and gold in the crust, far more than what is actually observed. The math was not fully aligning. The asteroidal delivery model accounted for a significant portion of surface water, but it could not fully explain the total volatile budget of the planet. Geologists began to ask an unsettling, revolutionary question. What if the delivery from space was only half the story? What if the delivery from space was merely the top layer of a much deeper internal reservoir? What if the Earth was never truly a dry vessel waiting to be filled? What if the primary source of our oceans did not fall from the blackness of the sky at all, but was already lurking beneath the surface, hidden within the burning heart of the planet, from the very moment of its creation? This radical shift in thinking opened up an entirely new chapter in planetary science, challenging everything we thought we knew about the birth of our world. If the internal water theory holds true, then the accretion of Earth was not a dry process at all. Instead, hydrogen molecules from the primordial solar nebula may have dissolved directly into the deep, churning magma ocean during the earliest stages of planetary assembly. Under immense core pressures, this trapped hydrogen would react with iron oxides in the silicate melt, forming trillions of tons of H2O directly within the planetary interior. This internal water reservoir would remain trapped beneath hundreds of miles of solid rock, safe from the stripping effects of early solar winds and solar radiation. It would mean that Earth was born pregnant with its oceans, holding the chemical ingredients for life within its deep mantle, waiting for the crust to cool so it could purge that moisture upward. Thus, the late heavy bombardment was not the sole creator of Earth's hydrosphere, but rather an additional layer applied on top of an already water-rich planet. The asteroids did not build the ocean from scratch. They supplemented a subterranean ocean that was already fighting to break through the basalt skin. The true story of Earth's water is therefore a dual narrative, a collision between cosmic fire raining down from above and primordial steam pushing up from deep below. As these two mechanisms converged, the atmosphere of Earth transformed into a massive pressure cooker. The stage was set for a planetary outgassing event on a scale unprecedented in our solar system's history. Millions of cubic kilometers of water vapor were accumulating in the dark sky, setting the stage for the greatest rainstorm the world would ever witness. While the asteroid delivery model answered key chemical questions, a growing group of geochemists began championing a radical alternative. They asked a fundamental question: what if Earth was born pregnant with its oceans? This is the inside job hypothesis, which suggests that water was not merely dusted onto a dry world by late-impacting asteroids, but was built directly into the planet's mantle during its earliest, most chaotic accretion phase. In this model, microscopic dust grains within the protoplanetary disk were not completely dry. Even inside the frost line, minute amounts of water vapor adsorbed onto the surfaces of silicate mineral grains. As these grains clumped together into pebbles, planetesimals, and eventually the proto-Earth, that moisture was drawn deep into the interior, trapped within the extreme gravitational squeeze of the forming planet. Under the staggering pressures and temperatures of the early mantle, hydrogen trapped inside the rock reacted directly with oxides, creating water chemically bound within solid minerals. This meant that while the surface was a scorched, glowing lava field, the mantle beneath held a colossal, hidden reservoir of volatile components. Earth wasn't an empty clay pot waiting for external rain. It was a pressurized, water-rich vessel waiting for a way to breathe its moisture out. For decades, testing this internal water theory seemed nearly impossible because humans cannot drill deeper than a tiny fraction of the Earth's outer crust. The deepest borehole ever constructed, the Kola Superdeep borehole, reached a depth of just 12 kilometers, barely scratching the planetary skin. How could scientists possibly verify what kind of water or minerals exist hundreds of kilometers down in the mantle transition zone? The breakthrough came through cutting-edge mineral physics and experiments using diamond anvil cells. By placing tiny samples of silicate minerals between the microscopic tips of two gem-grade diamonds, scientists can generate pressures exceeding 100,000 atmospheres and temperatures of thousands of degrees, perfectly replicating the extreme conditions found 400 to 600 kilometers beneath our feet. What researchers discovered inside these high-pressure chambers redefined our understanding of planetary geology. At these extreme depths, standard mantle minerals like olivine collapse and transform into a dense, bluish mineral known as ringwoodite. Crucially, ringwoodite acts like a high-density geological sponge. It does not contain liquid water in pockets or veins. Rather, it holds water in the form of hydroxide ions trapped directly inside its crystal lattice. The experimental data revealed that ringwoodite can hold up to 1.5% of its total weight in water. While 1.5% sounds modest, the sheer physical volume of the mantle transition zone, a vast sphere of rock hundreds of kilometers thick, means that if ringwoodite is saturated, there is a hidden reservoir of water inside the Earth equal to 1 to 3 times the total volume of all surface oceans combined. Physical evidence for this deep subterranean ocean arrived in a remarkable way. Geologists analyzing a scarred, low-quality diamond brought up from deep volcanic pipes in Brazil discovered a tiny, microscopic inclusion trapped inside the gem as it formed hundreds of kilometers down. That inclusion was a real, natural sample of ringwoodite. When scientists analyzed the tiny crystal, they confirmed it was saturated with water bound within its structure. This was definitive, physical proof that deep inside the Earth's transition zone lies a vast reservoir of hydration, an ancient, internal ocean that has been trapped beneath the crust since the planet was forged. This discovery revolutionized our perspective on the history of Earth's water. The oceans resting on our surface are not the whole story. They represent merely the upper layer of a continuous global water cycle that extends deep into the lower mantle. Water was present at the birth of the planet, survived the violent heat of formation, and lay in wait inside the solid rock. With vast reservoirs of water trapped inside the upper and lower mantle, the cooling of the post-impact Earth triggered the next phase of oceanic creation: massive, sustained planetary outgassing. As the global magma ocean slowly crystallized from the bottom up, water and other volatiles were forced out of the solidifying rock and into the remaining liquid melt. This process created immense internal gas pressures. Thousands of hyperactive volcanic vents, fissure eruptions, and massive magma plumes ripped open across the brittle basaltic crust. They did not merely spew molten lava, they acted as colossal exhaust pipes, releasing trapped subterranean gases into the primordial sky. The main gas spewing from these ancient volcanic vents was superheated steam. Billions of tons of water vapor were pumped into the atmosphere every single hour, accompanying thick plumes of carbon dioxide, nitrogen, carbon monoxide, and hydrogen sulfide. The young planet was degassing its interior, bleeding its deep moisture outward to build a dense atmospheric envelope. This primordial atmosphere was dark, heavy, and suffocating. Atmospheric pressure at the surface was dozens of times greater than modern sea level pressure, creating a dense thermal blanket that wrapped the entire globe. The sun, still young and relatively faint, was obscured by an unbroken, planetary cloud deck stretching thousands of miles high. As long as the crust remained white-hot or glowing red, this atmospheric steam could not condense. Any water droplets attempting to form in the lower atmosphere would evaporate instantly before touching the ground, radiating heat back into space. The planet existed in a state of atmospheric stagnation, a world wrapped in steam, waiting for its surface temperature to drop below a critical physical threshold. For millions of years, this atmospheric steam blanket insulated the planet, slowly radiating heat into the cold void of space. Step by slow step, the thermal balance of the Earth shifted. the heat loss to space gradually exceeded the radioactive and internal heat supplied by the mantle, causing the surface rocks to cool from incandescent red to a dull, cold black. When the surface temperature of the basalt crust finally dropped below the critical boiling threshold of water under high atmospheric pressure, a monumental physical transformation occurred. The superheated steam in the upper atmosphere began to cool and condense into actual liquid water droplets. High above the silent black landscape, the continuous global cloud deck darkened. Microscopic water droplets coalesced into massive rain clouds, spanning from pole to pole. The conditions were finally aligned for the greatest meteorological event in the history of the world. The first drops of liquid water began to fall from the sky. When they hit the warm basalt crust, many evaporated instantly, returning to the clouds as steam in a rapid, continuous cycle. But as the rain continued relentlessly, it carried thermal energy away from the rock, cooling the surface even faster. Soon, the drops no longer evaporated upon contact. They pooled in tiny cracks, trickled across jagged volcanic slopes, and ran down into low-lying impact basins. The sky broke open entirely, unleashing a torrential, planetary downpour that would not stop for thousands of years. This was the Great Deluge, a continuous, global storm of rain that flooded the newborn world. Thunder roared across an empty, dark landscape as lightning split the orange sky. Rivers of warm water carved paths through black volcanic stone, filling every low-lying basin, crater impact site, and tectonic rift. As thousands of years of relentless rain wore on, the shallow pools joined together to form vast, interconnected lakes. The lakes overflowed, drowning low-lying basalt plains and spreading out across the entire sphere. The primordial dry rock was disappearing beneath a rising expanse of warm, dark water. By the time the clouds finally began to thin and the torrential rain subsided, the Earth was unrecognizable. The scorched, glowing fireball of the Hadean Aeon was gone. In its place floated a serene, dark water world, covered almost entirely by a vast primordial ocean, ready to begin the next chapter of its evolution. This planetary rain did not fall onto clean, neutral ground. It washed over millions of square kilometers of raw, freshly minted volcanic basalt. As the hot acid rain pelted the basalt, it triggered aggressive chemical weathering on a global scale. Soluble ions, sodium, magnesium, calcium, and potassium, were dissolved out of the rock matrix and carried by torrential runoff into the gathering basins. Chlorine gas outgassed from volcanoes dissolved into the surface water as hydrochloric acid, quickly neutralizing into chloride ions. When paired with the abundant sodium leached from the basalt, these ions synthesized sodium chloride, common salt. Thus, the vast rainstorm didn't just fill the planetary ocean basins with pure distilled water, it created a rich, saline chemical broth from day one. The accumulation of this global saline reservoir altered the thermodynamics of the young Earth. Liquid water has an extraordinarily high specific heat capacity, meaning it can absorb and hold vast amounts of heat energy without experiencing drastic shifts in temperature. As the global oceans filled, they became the ultimate thermal buffer for our world. The oceans stabilized global temperatures, evening out the wild temperature swings between day and night, absorbing equatorial heat and distributing it toward the cooler polar regions. The chaotic, steam-filled greenhouse atmosphere was transformed into an organized, circulating hydrological cycle driven by evaporation, condensation, and oceanic currents. Furthermore, as the global water layer deepened, it exerted immense mechanical pressure on the thin basaltic crust beneath. Millions of tons of water pressing down on tectonic plates began to alter the mechanical dynamics of the upper mantle. Water seeped into deep geological faults, lowering the melting point of mantle rocks and acting as a vital lubricant for planetary movement. Without this massive surface volume of water, the Earth's crust might have locked into a rigid, stagnant lid like that of Venus or Mars. Instead, the weight and lubricating properties of the new oceans laid the groundwork for active plate tectonics, the geological motor that continuously recycles elements, builds continents, and regulates atmospheric carbon over billions of years. The birth of the ocean was therefore not merely the passive accumulation of liquid in a rocky basin, it was the activation of Earth's engine, a dynamic feedback loop linking the deep mantle, the surface crust, the atmosphere, and the climate into a single, living geological system. Every drop of rain that fell during the Great Deluge helped forge the planetary machinery that keeps our world stable today. When the clouds of the Great Deluge finally parted, they revealed a world that would be utterly unrecognizable to human eyes. The Earth around 4 billion years ago was not a lush green paradise, nor was it the blue and white marble we see from orbit today. It was an eerie, alien water world, a boundless, dark expanse of sea, stretching unbroken from horizon to horizon. There were no continents. Mountain ranges like the Himalayas or the Andes lay far in the unimaginable future. Only a few chains of dark, violent volcanic islands poked above the waves, spewing ash and glowing basalt into a turbulent sky. The ocean itself was not the vibrant turquoise or sapphire blue of modern seas. It was a deep, rich olivine green. This surreal green color was caused by massive concentrations of dissolved iron. The young, oxygenless ocean was saturated with soluble ferrous iron leaching out of the unweathered basaltic seafloor. Without free oxygen in the atmosphere, or water to rust this iron into red oxides, it remained dissolved in high concentrations, tinting the global ocean a striking green. Looking up from the surface of this green sea, the sky was equally strange. The air held no oxygen. Instead, a thick, hazy canopy dominated by nitrogen, carbon dioxide, and dense methane wrapped the planet in a heavy, orange-tinted fog. The sun, about 30% fainter in its youth than it is today, shone as a dull yellow disk, struggling to penetrate the hydrocarbon haze. The tides on this primordial water world were staggering. Because the moon had formed much closer to Earth during the giant impact eon, it loomed monstrously large in the sky, orbiting at a fraction of its current distance. Its intense gravitational pull created wild, catastrophic global tides. Bulges of green seawater hundreds of feet high swept across the open ocean every few hours, crashing against the solitary volcanic island arcs with terrifying kinetic force. These massive tides scoured the volcanic rocks, accelerating the dissolution of minerals and further enriching the global chemical soup. Despite the eerie appearance of this alien landscape, a critical chemical transformation was occurring within the depths of the Green Sea, the titration of planetary salinity. As the Great Deluge poured acid rain onto the basaltic crust, it reacted continuously with minerals, leaching out immense quantities of metal cations, sodium, potassium, calcium, and magnesium. Simultaneously, volcanic outgassing dumped gaseous hydrogen chloride, carbon dioxide, and sulfur dioxide directly into the sky, which dissolved into the falling rain as acids. When these acidic waters washed into the ocean basins, they met the dissolved metal ions, undergoing neutralization reactions that generated neutral salts, predominantly sodium chloride. This chemical balance was crucial. If the oceans had remained too acidic, complex organic molecules would have been rapidly torn apart by acid hydrolysis. If they had become overly alkaline, essential trace metals like zinc and iron would have precipitated out of solution, becoming inaccessible to early chemical processes. Through millions of years of continuous rock weathering and oceanic circulation, the Earth naturally self-regulated. The oceans settled into a moderately saline, neutral to slightly acidic pH balance, a stable, universal aqueous solvent perfectly primed for prebiotic chemistry. Deep at the bottom of this global green ocean, miles beneath the violent surface tides, the ocean floor was torn open by deep tectonic fractures. Cold seawater seeping into cracks in the thin basaltic crust traveled down toward the hot mantle, where it was superheated to hundreds of degrees Celsius. These superheated fluids, stripped of oxygen and enriched with hydrogen, methane, hydrogen sulfide, and dissolved transition metals, erupted back out of the seafloor in towering structures known as hydrothermal vents. Far removed from the harsh ultraviolet radiation of the sun, these deep vents created localized sanctuaries of intense thermal and chemical energy. Among these submarine features were alkaline vents, constructed from porous carbonate minerals full of microscopic, interconnecting labyrinths. As warm, alkaline fluids from the vent met the slightly acidic, iron-rich seawater of the Hadean Ocean, natural proton gradients formed across the thin mineral walls of these microscopic pores. These natural proton gradients were physically identical to the electrochemical gradients that every living cell uses today to power ATP synthesis. The hydrothermal vents acted as natural geochemical batteries, driving the synthesis of amino acids, nucleotides, and simple lipid membranes within their tiny mineral chambers. The global ocean was no longer just a vast reservoir of liquid water. It had become the ultimate incubator. Water provided the liquid medium where organic molecules could dissolve, collide, and organize without being destroyed by solar radiation. The primordial soup was simmering in the dark depths of a green world. From these deep hydrothermal cradles, the first self-replicating molecular chains emerged. Life did not start on dry land or in shallow, sunlit puddles, but in the crushing dark pressures of the early ocean floor, protected by miles of green seawater above. Water was the solvent, the shield, and the transport mechanism for the dawn of biology. As primitive single-celled organisms spread through the water column, they began interacting with the hydrosphere in ways that would alter the planet forever. Eventually, early photosynthetic microbes evolved, using the abundant water molecules as electron donors, splitting them apart with sunlight and releasing a toxic waste product into the sea, pure oxygen gas, O2. This oxygen didn't enter the atmosphere immediately. First, it reacted with the vast reservoir of dissolved ferrous iron in the green ocean. The iron oxidized, turning into rust and raining down onto the ocean floor in thick, rusty layers of iron oxide over hundreds of millions of years. These massive iron deposits formed the banded iron formations that humanity mines today for steel. As the dissolved iron was filtered out of the water, the green ocean cleared, turning into the clear blue sea we know today. Once the ocean's iron was fully oxidized, oxygen began escaping into the atmosphere, building the ozone layer and transforming Earth into an oxygen-rich haven. The origin of our oceans was not merely a physical event, it was the prerequisite for a living world. From a dry, accretionary fireball to a steam-choked pressure cooker, and finally to a blue marble swathed in liquid, Earth's journey was guided at every step by the unique behavior of water. Today, as we look at a simple glass of tap water, we are looking at an ancient chemical survivor. The water in your glass was forged in the cold depths of the interstellar cloud, survived the violent birth of the sun, was trapped deep in the Earth's mantle, and exploded out of primordial volcanoes to fall as rain during a 10,000-year storm. It flowed through green, oxygenless seas, washed over the bodies of long-extinct organisms, and carried the thermal pulse of our planet across billions of years. We do not just live on a world with water, we are walking, breathing containers of that same primordial ocean, bound forever to the secret, epic history of the liquid that built our home. Consider the sheer scale of the global hydrological transformation as this green expanse matured. Over millions of square kilometers, the ocean acted as a giant planetary heat sink. Solar radiation hitting the surface ocean was redistributed across latitudes by deep wind-driven surface currents and density-driven thermohaline circulations. This circulation prevented the equator from becoming an unlivable furnace and kept the polar regions from freezing solid under the faint young sun. The ocean was actively regulating the global thermals, establishing a planetary thermostat that would remain remarkably stable for 4 billion years. Without this massive fluid blanket, Earth's climate would have swung between extreme, lethal boundaries. Instead, the high thermal inertia of liquid water created a buffered climate, smooth enough for fragile biochemical assemblies to survive and evolve without being destroyed by massive temperature swings. As water continued to cycle through subduction zones and volcanic arcs, it also stripped vast quantities of carbon dioxide out of the atmosphere. CO2 dissolved directly into seawater, reacting with dissolved calcium to form insoluble calcium carbonate, which settled down onto the abyssal ocean floor as thick limestone sediments. This carbon sequestration process permanently drew down the suffocating greenhouse gas envelope, clearing the sky and lowering atmospheric pressures to levels comfortable for life. The oceans were not merely storing water, they were scrubbing the air, converting a toxic atmosphere into a breathable sky. Every wave crashing against those ancient basaltic shores was performing work, breaking down rock, balancing chemistry, trapping carbon, and transferring energy. The oceans were the ultimate geological engines, driving the geochemical evolution of the entire planet. When we reflect on this immense journey, we realize that liquid water is not just an accidental feature of Earth's geology, it is the defining character of the planet itself. From the nuclear heart of stellar clouds to the deep interior of our planet's mantle, the story of water is the story of Earth's creation. The green ocean of the early Archean eon was far more than an impressive body of liquid. It was a boundless reservoir of a chemical compound so strange and anomalous that its mere existence defies standard physical expectations. Water is, by all accounts, a bizarre substance. To truly understand how this fluid transformed our planet, we must look down to the subatomic scale, to the precise arrangement of hydrogen and oxygen atoms that make up every drop. A single molecule of water is shaped like a tiny, bent V. The single oxygen atom holds an intense electronegative pull, dragging the shared electrons away from the two smaller hydrogen atoms. This asymmetry creates a distinct dipole moment, a permanent electrical imbalance, where the oxygen side carries a faint negative charge, while the hydrogen ends carry a positive charge. This subtle dipole moment is the secret engine behind every ocean on Earth. Because opposite electrical charges attract, individual water molecules lock together through hydrogen bonding. These transient, sticky bonds act like an invisible cosmic glue, holding liquid water together across a vast temperature range where almost any other light molecule of similar mass would exist strictly as a gas. Without hydrogen bonding, water would boil into steam at -80 degrees Celsius. The Earth would be completely unable to hold onto liquid oceans at ambient temperatures. Every sea, river, and lake on our planet exists solely because this subatomic electrical attraction prevents H2O from evaporating instantly into the cold vacuum of space. Furthermore, these hydrogen bonds give water another unique physical anomaly. Its maximum density occurs not when it freezes into a solid, but when it is a liquid at 4 degrees Celsius. As water cools toward its freezing point, its molecules expand into an open, hexagonal crystal lattice. This makes solid ice less dense than liquid water, causing ice to float. In planetary science, floating ice is a crucial prerequisite for a stable climate. If ice were denser than liquid water, like almost every other frozen chemical compound in the universe, sea ice would sink to the ocean floor as soon as it froze. deep ocean floors would accumulate endless miles of solid ice, shielded forever from the warm rays of the sun, eventually turning the Earth into a completely frozen snowball world. Instead, because ice floats, it forms an insulating thermal blanket on top of seas and lakes. Floating ice traps the internal heat of the ocean beneath it, protecting liquid water ecosystems in the deep abyssal zones even during the coldest ice ages. Water protects itself from freezing solid from the top down, keeping the planetary circulatory system moving beneath the ice sheets. Beyond its thermal behavior, water possesses an unmatched capacity as a universal solvent. Its polar structure allows it to pry apart ionic compounds, like salts and minerals, dissolving raw rock into liquid chemical solutions. As seawater circulates through the planetary crust, it extracts vital trace elements, magnesium, calcium, phosphorus, and iron, and carries them throughout the vast global ocean. This solvent ability allowed the early ocean to act as a massive chemical reactor. Microscopic organic building blocks dissolved easily within the water column, tumbling through warm currents and encountering one another far more frequently than they ever could on dry stone or in open air. Water was not just a container for chemical reactions, it was the active facilitator of prebiotic life. As the global ocean interacted with the cool basaltic crust during the early Archean eon, it began to drive an immense, deep-seated geological engine, the planetary water recycling system. Seawater, seeping miles down into subduction zones, entered areas of crushing pressure and high heat, where tectonic plates plunged down into the burning mantle beneath. When wet, hydrated oceanic crust sinks into the mantle, the extreme heat squeezes the water out of the rock. This liberated water acts as a fluxing agent, dramatically lowering the melting temperature of the surrounding mantle rock. The hydrated rock melts much faster, generating buoyant magma plumes that rise upward to feed explosive volcanoes along continental arcs. This process forms granitic rock, a lighter, less dense type of stone than basalt. Over hundreds of millions of years, as granitic magma rose continuously to the surface, it accumulated into thick, buoyant continental slabs that sat high above the heavy basaltic seafloor. Liquid water was literally carving out the first permanent continents from the ocean floor. Without liquid oceans to hydrate sinking slabs, plate tectonics as we know it would lock up entirely. Water acts as the essential physical lubricant between moving continental plates. It hydrates fault lines, reduces mechanical friction, and allows the rigid outer shell of the Earth to split, slide, and subduct smoothly over geological timescales. We can see the grim consequences of a waterless world by looking at Venus. Venus possesses a mass and density nearly identical to Earth, but because it lost its primordial surface water to runaway atmospheric evaporation, its crust became rigid, thick, and immobile. Venus locked into a stagnant lid regime, trapping heat beneath its crust until the entire planet ruptures in catastrophic global volcanic floods. Earth avoided this hellish fate because its oceans continuously lubricated the subduction zones. The ocean acts as a dynamic conveyor belt, carrying surface water deep into the mantle and receiving it back millions of years later through volcanic outgassing and mud volcanoes. The surface oceans and the deep interior mantle exist in a continuous, endless dialogue. This deep hydrologic cycle means that the ocean you see today is not static. It is continuously drained into the planetary interior and continuously replenished by deep mantle plumes. Over a cycle of roughly 1 billion years, an entire ocean's worth of water passes completely through the deep rocky mantle before returning to the surface. As this continuous cycle churned through the early Archean eon, it also regulated the atmosphere. Carbon dioxide dissolved in seawater reacted with minerals to form thick limestone beds, locking atmospheric carbon down inside the crust. This drawdown prevented the Earth from experiencing a runaway greenhouse effect like Venus. balancing global temperatures even as the sun grew steadily brighter. By 4 billion years ago, the blue planet had developed a fully integrated, self-regulating ecosystem. The unique molecular properties of water, combined with deep subduction recycling, had forged a dynamic, stable environment where life could take hold, adapt, and transform the entire biosphere. This delicate chemical and physical equilibrium transformed water into the planet's ultimate climate manager. High specific heat capacity meant the global ocean absorbed immense quantities of thermal energy without undergoing rapid temperature spikes. Equatorial seas soaked up excess solar flux, driving massive oceanic currents that redistributed that thermal energy toward the polar zones. This fluid conveyor belt prevented extreme temperature gradients across the globe, smoothing out seasonal swings and ensuring that equatorial waters never boiled while polar regions remained accessible to liquid circulation. The oceans acted as Earth's dynamic heat engine, stabilizing global weather systems and maintaining a habitable thermal zone across vast geological epochs. Deep below the waves, where oceanic plates converged and squeezed under extreme forces, vast fields of submarine mud volcanoes erupted. These hydrothermal mud vents spewed slurry enriched with serpentine minerals, created when seawater reacted directly with olivine-rich mantle rocks in a process known as serpentinization. Serpentinization reactions released massive volumes of molecular hydrogen directly into the deep sea. This hydrogen provided an abundant energy source for early chemosynthetic microorganisms, offering a reliable, light-independent metabolic fuel deep within the sunless ocean floor. Seawater was actively feeding the primitive biosphere from below. As subduction continued to draw wet sediments deep into the Earth's crust, the water liberated at depth didn't just generate granitic magma, it altered the structural density of the entire continental lithosphere. Hydrated continental roots grew buoyant, thick, and resistant to recycling, ensuring that once continents formed, they remained floating above the dense oceanic crust. This continental emergence altered global topography forever. Rain falling on newly exposed landmasses initiated river systems, carving channels through dry rock, eroding minerals, and washing vast quantities of sediment back down into the ocean basins. The modern cycle of continental erosion, marine sedimentation, and subduction recycling was fully established. Without the continuous action of water driving this cycle, Earth's surface would have remained a flat, dark expanse of submerged basalt. Water provided the mechanical force to build continents, carve topography, and create diverse coastal environments where shallow water life could flourish alongside deep-sea hydrothermal communities. Every drop of moisture cycling through this grand system carried a microscopic history of the planet's evolution. Water moved from the sky to the surface, through the deep mantle, out through explosive volcanoes, and back into the atmosphere in an unbroken, multi-billion-year loop. It is this endless recycling process that keeps our world alive. The water in our lakes, the water in our atmosphere, and the water locked deep within our cells are all connected to this deep geological circuit, maintaining the delicate balance that allows Earth to remain a thriving, blue sanctuary floating in the cold void of space. The unique properties of liquid water on Earth become even more profound when we look beyond our own sky and cast our eyes out toward the frozen, quiet edges of the outer solar system. For centuries, humanity assumed that liquid water was a rare privilege reserved exclusively for Earth, a delicate reward for sitting in the astronomical sweet spot known as the Goldilocks zone. We believed that if a world orbited too close to its host star, its oceans would boil away, and if it orbited too far, its water would freeze into solid, lifeless stone forever. Yet, modern space probes have shattered this terrestrial bias completely. Out in the cold, dark depths of space, far beyond the sun's frost line where solar radiation is too weak to melt a single grain of ice, liquid oceans are hiding in plain sight. They do not rest openly under a warm sky. Instead, they exist deep beneath thick, frozen crusts on the icy moons of the giant gas worlds. Consider Europa, the smooth, pale moon orbiting Jupiter. Encased beneath a shell of solid water ice, tens of kilometers thick, lies a global, subsurface liquid ocean containing more than twice the total volume of all Earth's oceans combined. Europa sits far outside the traditional habitable zone, receiving almost no solar warmth. Yet its ocean remains liquid, kept warm by the immense gravitational tidal forces exerted by Jupiter's colossal mass. As Europa travels along its elliptical orbit, Jupiter's gravitational pull constantly flexes and stretches the moon's rocky core like a rubber ball. This continuous gravitational kneading generates immense internal friction and heat. This thermal energy warms the base of Europa's rocky mantle, driving submarine hydrothermal vents that keep a vast, dark, liquid ocean churning beneath miles of ice. Even further out, orbiting Saturn, lies tiny Enceladus. Despite being no larger than the United Kingdom, Enceladus is one of the most hydrologically active bodies in the entire solar system. Spacecraft have photographed giant plumes of water vapor and ice crystals blasting hundreds of miles out into space from deep fractures near its south pole. When sampling these ice plumes, instruments detected dissolved salts, simple organic compounds, silica microparticles, and molecular hydrogen. This chemical signature is undeniable proof that deep beneath Enceladus's frozen crust lies a warm, saline ocean in direct physical contact with a hot, hydrothermal rocky core. The very same hydrothermal conditions that catalyzed the origin of life in Earth's primordial green seas are actively occurring right now inside icy moons scattered across the outer solar system. This realization transforms our understanding of the cosmos. Liquid water is not a fragile, surface-bound anomaly unique to Earth. It is a universal phenomenon. The universe is dripping with liquid oceans, tucked safely inside icy planetary vaults, shielded from the vacuum and radiation of space. Yet, while these ocean moons hold vast quantities of hidden water, our planet remains uniquely gifted. Earth is the only world where liquid water exists openly on the surface, exposed to the atmosphere, interacting dynamically with sunlight, plate tectonics, and a living biosphere. This dynamic surface ocean does not merely surround us, it defines us from the inside out. Every living organism on Earth is essentially a mobile container of primordial seawater. The human body is roughly 60% water by weight. Our brains and hearts are nearly 3/4 liquid. The chemical composition of human blood plasma, its balance of water, sodium, potassium, and chloride ions, mirrors the ancient saline ratios of the early Archean Ocean. When life eventually crawled out of the sea and onto dry land hundreds of millions of years ago, it could not leave the ocean behind. Instead, it took the ocean along inside itself, encapsulating liquid salt water within biological membranes to carry it across dry terrain. Every time you take a sip from a glass of water, you are connecting directly with this epic planetary lineage. The water entering your body is unkillable and immortal. It cannot be truly consumed or destroyed. It can only be borrowed for a brief moment before it cycles back into the global flow. The exact water molecules passing through your glass tonight may have once been trapped in the crystal matrix of a carbonaceous asteroid 4.5 billion years ago. They may have erupted as superheated steam from a Hadean volcano, fallen as acid rain during the Great Deluge, or washed through the gills of ancient marine organisms in a green, oxygenless ocean. This water has floated as high-altitude atmospheric ice clouds over forgotten supercontinents, locked itself inside glaciers during global ice ages, and spent millions of years circulating through the deep, sunless mantle transition zone. It has been filtered, evaporated, condensed, and recycled countless times across geological eons. Even as we enjoy this abundant liquid, the Earth is slowly, silently leaking its water into space. High in the upper atmosphere, intense solar ultraviolet radiation continuously strikes water molecules, splitting them apart into free hydrogen and oxygen. The lightweight hydrogen atoms frequently reach escape velocity, bleeding away into the cosmic void forever. Every year, thousands of tons of primordial hydrogen slip past Earth's magnetic shield and drift into interstellar space. Our oceans are undergoing an excruciatingly slow, imperceptible planetary evaporation over billions of years. As the sun continues to grow hotter and brighter, this atmospheric loss will gradually accelerate. In the distant geological future, far beyond our lifetime, the great hydrological cycle will eventually slow down and stall. The oceans that built our world, lubricated our tectonic plates, and nurtured our biology will slowly dry up, returning Earth to a quiet, dry, rocky sphere floating in space. But tonight, the oceans are full, vibrant, and alive. They stretch across thousands of miles, crashing against dark coastlines, driving global weather systems, and holding the vast majority of our planet's living biomass. The story of Earth's water is the ultimate epic, a journey born in cosmic fire, forged in planetary violence, delivered by space rocks, and preserved inside our very cells. Beyond our immediate neighborhood in the solar system, astronomical observations of distant exoplanetary systems reveal that water is one of the most abundant compound molecules in the cosmos. Spectroscopic analysis of light filtering through the atmospheres of alien planets reveals clear signatures of water vapor drifting across worlds hundreds of light-years away. Some of these distant exoplanets, known as hyperdense ocean worlds or Hycean planets, are covered entirely in oceans hundreds of miles deep, lacking any solid landmass whatsoever. On these worlds, the pressure at the bottom of the ocean is so immense that water is forced into exotic solid states of matter, such as Ice 7 and Ice X, even at high temperatures. These alien ocean architectures prove that water's ability to adapt under planetary conditions spans a vast physical spectrum. Whether forming hyperdense, high-pressure ice cores on massive exoplanets or circulating through thin surface oceans like Earth's, water remains the primary medium through which planetary systems organize their thermal and chemical energy. Back on Earth, this universal solvent plays an ongoing role in modulating the delicate atmospheric envelope that shields us from cosmic radiation. Water vapor is the most potent greenhouse gas in Earth's atmosphere, responsible for trapping a significant portion of the planet's thermal radiation and keeping global average temperatures in a stable, habitable range. Without atmospheric water vapor creating a natural blanket, Earth's surface temperature would drop precipitously, freezing the surface oceans solid even with the modern sun shining overhead. The continuous evaporation of ocean water into the lower atmosphere creates a self-regulating thermal feedback loop that prevents extreme temperature collapse. This evaporative flux drives the global weather machine. As warm water evaporates from tropical oceans, it ascends into the troposphere, releasing immense latent heat as it condenses into clouds. This latent heat release fuels atmospheric circulation cells, trade winds, and jet streams that move weather systems across continents. Rainfall returning to the land carries dissolved atmospheric gases and ions back down into terrestrial ecosystems, carving river valleys, replenishing subterranean aquifers, and feeding the planetary hydrogeological engine. Every drop of rain is an active participant in an unbroken global circuit, connecting the mantle, the surface, the atmosphere, and the cosmos. As humanity looks toward the future of space exploration, water remains the ultimate target and currency. Finding ice deposits on the Moon, Mars, and near-Earth asteroids is the single most critical factor for sustaining long-term human presence in deep space. Water provides drinking supplies, radiation shielding, oxygen for breathing, and liquid hydrogen and oxygen for rocket propellant. The same molecule that allowed life to emerge in Earth's Hadean seas will be the precise element that allows life to travel to other worlds. We are bound to this extraordinary fluid across every dimension of our existence, past, present, and future. When you look out across the dark expanse of the sea, or simply listen to the quiet, rhythmic sound of falling rain outside your window, you are listening to the heartbeat of our world. You are witnessing the ancient liquid that made us who we are, continuing its endless, beautiful journey around the blue marble we call home. The architecture of the internal ocean is one of the most profound realities of human biology. To stand on the surface of the Earth and look out at the endless blue horizon of the sea is to gaze into a mirror. We do not merely inhabit a world dominated by liquid water, we are constructed from it. The vast global ocean that churned in darkness during the Archean Eon did not disappear when life colonized the dry continents. It simply partitioned itself into trillions of microscopic biological vessels. Every human cell is a self-contained aquatic ecosystem. The cytosol, which is the fluid matrix filling the interior of your cells, is a carefully managed salt solution whose elemental ratios reflect the ancient chemistry of the early seas. Inside this microscopic fluid medium, cellular machinery operates in perpetual motion. Enzymes, proteins, and strands of genetic material do not collide by chance in a dry vacuum. They drift, fold, and interact while suspended in a dynamic matrix of water molecules. The double helix structure of DNA relies directly on the hydrophobic and hydrophilic forces exerted by surrounding water molecules, forcing the genetic code into its resilient, twisting shape. Within the inner membranes of mitochondria, cellular respiration relies on the precise flow of hydrogen ions across a watery gradient to generate adenosine triphosphate, the universal energy currency of life. In the most literal biological sense, terrestrial life did not conquer the land by abandoning the ocean. It invented biological armor such as skin, membranes, and circulatory pathways to take the ocean with it. You are a walking piece of the ancient sea, carrying its thermal stability, its salinity, and its chemical complexity across the dry continents. Nowhere is the dynamic power of water more intricate or profound than within the human brain. Suspended inside the dark vault of the cranium, the brain floats within a continuous reservoir of cerebrospinal fluid, a clear, saline liquid derived directly from blood plasma. The brain does not simply rest on bone, it neutrally floats inside this liquid cushion. This buoyancy reduces the effective weight of the 1,500-gram human brain to a mere 50 grams, preventing its delicate neural architecture from collapsing under the unrelenting force of gravity. Every thought, memory, sensory perception, and emotion you experience is fundamentally an electrical pulse powered by the movement of dissolved ions in water. When a neuron fires, microscopic channels in its membrane open, allowing sodium and potassium ions to rush across a liquid barrier. This ionic surge generates the action potential, which is the spark of biological electricity that travels down the axon. Without liquid water serving as the solvent to hold these ions in solution, neural communication would freeze instantly. The human mind is, at its core, a constellation of electrical signals cascading through a specialized, structured ocean. As night falls and the body grows quiet, liquid water undertakes one of its most vital maintenance operations within the central nervous system through glymphatic clearance. During waking hours, the intense metabolic activity of billions of firing neurons accumulates cellular debris, including metabolic waste products like beta-amyloid proteins. When you sink into deep, slow-wave sleep, the structural configuration of the brain shifts dramatically. During deep non-REM sleep, the extracellular space within the brain expands by roughly 60%. Cerebrospinal fluid rushes through the neural architecture like an arterial tide, washing through interstitial spaces and flushing accumulated metabolic waste into the venous system. This nighttime cleansing cycle is a literal washing of the mind. It requires vast volumes of liquid water moving in rhythmic, synchronized waves through microscopic channels in neural tissue. Without this nightly hydraulic flushing, toxic protein aggregates accumulate, impairing cognitive function and compromising neural health. Sleep is the time when the internal ocean cleanses itself, resetting the biological clock and restoring the delicate biochemical balance required for another day of conscious awareness. To appreciate the scale of this planetary fluid, we must zoom back out from the microscopic pathways of the human brain to the vast thermodynamic engine of the global atmosphere. Liquid water possesses one of the highest specific heat capacities of any naturally occurring substance on Earth. This extraordinarily high value means that water can absorb or release vast quantities of thermal energy with only minimal changes in its own temperature. Equatorial oceans soak up intense solar radiation, preventing tropical runaway heating. Thermohaline circulation drives deep-sea currents, often referred to as the global conveyor belt, to move heat toward the poles. Atmospheric evaporation converts liquid to vapor, transferring immense thermal energy into the upper troposphere. Meanwhile, polar ice caps reflect incoming solar radiation back into space, maintaining global cold reservoirs. This global heat pump acts as Earth's master climate buffer. Tropical ocean waters absorb excess solar heat and transport it thousands of miles toward the poles via major surface currents like the Gulf Stream. As warm water reaches polar latitudes, it cools, increases in density, and sinks into the abyssal depths, driving the deep thermohaline circulation. This is a massive, three-dimensional oceanic conveyor belt that takes over 1,000 years to complete a single circuit around the globe. When we trace the full trajectory of water, from its synthesis in the outer envelopes of ancient dying stars, to its arrival on the primordial Earth via planetesimal impacts, a profound realization emerges. Water is not merely a passive material environment in which planetary geology and biological evolution happen to occur. Water is the primary actor. In geology, water lubricates subduction zones, lowers mantle melting points, drives volcanic arc formation, builds continents, and prevents stagnant lid planetary paralysis. In chemistry, water acts as the supreme polar solvent, dissolving raw rock into mineral-rich solutions that feed chemosynthetic and photosynthetic life. In biology, water structures cellular membranes, catalyzes enzymatic reaction pathways, stabilizes genetic polymers, and enables neural signaling. In astronomy, water hides beneath the frozen shells of outer solar system moons like Europa and Enceladus, preserving vast subsurface oceans far beyond the classic circumstellar habitable zone. The journey begins with stellar nucleosynthesis forging oxygen, which combines with hydrogen to form interstellar ice grains. These grains coalesce into comets and asteroids, which deliver water to planetesimals through relentless impacts. Once on Earth, this fluid bifurcates into two interdependent systems. Part of it sinks into the crust via oceanic subduction, lubricating the mantle and driving plate tectonics. The other part enters the planetary atmosphere, generating global precipitation and fueling ecosystems. Ultimately, both pathways converge inside cellular life, giving rise to conscious thought and the human mind. The glass of water sitting on your bedside table tonight contains molecules that have existed for over 4.5 billion years. They were forged in the cold interstellar clouds before our sun was born. They have survived planetary accretion, Hadean magma oceans, continental collisions, glacial ice ages, and the rise and fall of countless biological eras. That water has been steam in volcanic plumes, ice in ancient ice sheets, ocean currents in lost primeval seas, and rain falling upon untouched forests. It has passed through the bodies of ancient organisms, cycled through the atmosphere, and fallen once again to nourish the living world. The global hydrological loop connects evaporation from oceans and vegetation directly to atmospheric condensation in clouds, which then releases precipitation as rain, snow, and dew. This moisture infiltrates subterranean aquifers and rivers, nourishing organisms before cycling back into the atmosphere and oceans. Every drop you consume is borrowed from this infinite planetary loop. It remains unkillable, indestructible, and forever in motion. Long after our cities have crumbled and our species has passed into the deep layers of the geological strata, the water will remain. It will continue to evaporate under the sun, condense into clouds, fall as quiet rain upon the ancient mountains, and circulate through the deep mantle of the planet. As you lie in the quiet dark, listening to the steady, rhythmic drum of rain falling against the glass outside, you are listening to the oldest sound on Earth. It is the sound of the planetary distillation engine working as it has for 4 billion years. It is the sound of the ancient ocean returning to the land, nourishing the soil, filling the rivers, and keeping the great biological dance alive. The story of water is the story of everything. It is the story of the cosmos, the planet, the cell, and the conscious mind. The cycle is complete. The long journey from the stars to the deep sea and into the quiet pulse of your own bloodstream has come to rest. Let the sound of the eternal rain carry you into the quiet, dreamless dark. You are home. The story of water on Earth is not merely a tale of past origins and present stability. It is an ongoing epic that reaches deep into the distant planetary future. As we cast our minds forward across vast geological eons, we realize that the blue world we inhabit today is living through a temporary, golden era of aqueous abundance. The continuous movement of water between the sky, the surface oceans, and the deep subterranean mantle is part of a dynamic system that will ultimately evolve, transform, and one day come to a quiet, natural end. To understand the long-term future of Earth's water, we must first look downward, deep beneath the ocean floor into the Earth's mantle transition zone. Far below the reach of sunlight, at depths between 400 and 600 kilometers, water is trapped within the crystalline lattice of high-pressure minerals like ringwoodite and wadsleyite. This deep mantle reservoir may hold as much water as all surface oceans combined. Through the continuous process of subduction, where oceanic plates slide beneath continental crust, billions of tons of seawater are dragged down into the mantle every year. At the same time, volcanic eruptions, mid-ocean ridges, and island arcs spew superheated steam back out into the atmosphere, returning that subterranean water to the surface cycle. For billions of years, this deep planetary exchange has maintained a delicate equilibrium. The amount of water pulled down into the tectonic engine has roughly matched the volume returned through volcanic outgassing. This global equilibrium has kept the surface oceans full, maintaining continental shorelines and preserving the stable sea levels required for complex biological life to flourish. However, as the Earth's interior gradually cools over cosmic timescales, this balance will subtly shift. A cooling mantle absorbs water more efficiently than it releases it through volcanism. Geologists estimate that over the next billion years, the net flow of water into the subduction zones may begin to exceed the volcanic return. Ocean water will slowly, imperceptibly drain down into the deep mantle rock, locked away in mineral crystals far beneath the crust. Seafloors will gradually widen, coastlines will retreat, and the vast open oceans will slowly shrink as the planet's internal sponge absorbs its own liquid surface. While the Earth's interior slowly draws water down from below, an even more powerful force will act upon the oceans from above, the relentless evolution of our own star. The Sun is a main sequence star powered by the nuclear fusion of hydrogen into helium at its core. As the core burns through its hydrogen fuel, it contracts and grows hotter, causing the sun's outer layers to slowly expand and brighten. Every billion years, the sun's luminous output increases by roughly 10%. This gradual rise in solar luminosity will set off a profound series of climatic transitions on Earth. In roughly 1 billion years, as the sun shines 10% brighter than it does today, the average surface temperature of our planet will climb significantly. Higher global temperatures will dramatically accelerate the rate of oceanic evaporation. Vast volumes of seawater will transform into atmospheric water vapor, loading the troposphere with a dense, humid blanket. Because water vapor is a potent greenhouse gas, this increase in atmospheric moisture will trap even more thermal radiation, driving surface temperatures higher still. This feedback loop marks the beginning of a critical transition in Earth's planetary life cycle. As the lower atmosphere becomes saturated with moisture, water vapor will begin to penetrate high into the stratosphere, a region that is currently extremely dry. In the upper atmosphere, exposed to the unfiltered glare of the sun, water molecules will meet their ultimate destruction through photolysis. High-energy solar ultraviolet radiation will strike the evaporated text molecules, severing the chemical bonds between hydrogen and oxygen atoms. The liberated hydrogen, being the lightest element in the universe, will easily reach escape velocity and bleed away into the vacuum of space, blown away by the solar wind. This continuous escape of hydrogen into space represents an irreversible loss of planetary water. Tons of primordial water, which originally arrived on Earth via ancient asteroid impacts during the dawn of the solar system, will drift out into the cosmic void forever. As the hydrogen escapes, the remaining oxygen will react with surface rocks, oxidizing the crust into a barren, rusty red landscape. Over hundreds of millions of years, this atmospheric escape will slowly bleed the oceans dry. The great marine basins, the Atlantic, the Pacific, the Indian Ocean, will gradually shrink into shallow, hypersaline lakes, separated by vast salt flats and exposed continental shelves. The vibrant marine ecosystems that have endured for hundreds of millions of years will contract into shrinking aquatic refuges. Eventually, as solar luminosity continues to climb, even these isolated saline lakes will boil away completely. The great hydrological cycle, which powered planetary weather, carved continental rivers, and sustained terrestrial biology for over 4 billion years, will come to a final halt. The clouds will dissipate, the rain will stop falling, and the Earth will transform into a warm, arid sphere of dry, wind-sculpted rock. Yet, even in this distant, waterless future, the legacy of Earth's primordial liquid will remain embedded in the very structure of the planet. The dry continental crust, the ancient river valleys carved into granite, and the mineral deposits scattered across dry seabed plains will forever bear the physical signature of the lost oceans. The water that once flowed through our rivers, filled our seas, and circulated through the cells of every living creature will have completed its planetary journey. Part of it locked deep within the subterranean mantle, and part of it drifting as silent, invisible hydrogen atoms across the interstellar night. To contemplate this distant cosmic horizon is not a cause for sorrow, but an invitation for profound awe and gratitude. It reminds us that we are privileged to exist during Earth's golden planetary spring, a precious geological window when the temperature is gentle, the atmosphere is rich, and the oceans are full. Tonight, the water is still here, abundant and serene. It flows quietly through our streams, rolls in vast waves across the dark oceans, falls softly as night rain upon our roofs, and flows through our very veins. As you rest in the quiet dark, listen to the gentle rhythm of the world outside. The ancient liquid that brought life to the cosmos is holding you safe, carrying you peacefully through the quiet night. As the sun's luminosity continues its relentless, upward march over the next billion years, the loss of Earth's surface oceans will fundamentally reshape the entire architecture of life on our world. Long after the open seas have evaporated into the upper atmosphere and bled away as hydrogen into the cold vacuum of space, water will not vanish completely from the planet. Instead, it will execute a dramatic, strategic retreat, drawing back into its ultimate biological and geological refuges deep beneath the Earth. Hundreds of meters beneath the baked, sun-scorched surface, deep subterranean fracture zones will remain saturated with ancient groundwater. Protected from the intense, unfiltered ultraviolet radiation above, microbial communities, extremophiles capable of deriving energy from radiolytic hydrogen and mineral oxidation will endure in these dark, liquid pockets for hundreds of millions of years after the surface has become an arid, wind-swept desert. At the extreme poles, deep basinal troughs may hold concentrated, hypersaline brine pools tucked under thick blankets of protective sediment. These ultra-dense liquid reservoirs will stubbornly resist boiling, serving as the final surface-level oases on a steadily warming planet. These hidden aquatic environments represent the final chapter of Earth's surface biosphere. They stand as a quiet, microscopic echo of the ancient, vibrant oceans that once covered the world from pole to pole. Yet, when we look beyond the ultimate horizon of our own solar system, the story of water expands from a local planetary tale into a universal narrative. Astronomical observations across our galaxy confirm that water is not a rare terrestrial jewel, but a primary structural building block of the entire cosmos. Water molecules form continuously in the interstellar medium, where dying red giant stars eject massive amounts of oxygen into interstellar gas clouds rich in primordial hydrogen. Dust grains floating in these cold molecular clouds act as surface chemical catalysts, allowing hydrogen and oxygen to combine into frozen ice mantles long before new stars or planets even begin to form. When these massive interstellar clouds eventually collapse under gravity to form new star systems, this cosmic water is incorporated directly into young protoplanetary disks. Inside what astronomers call the snow line, the thermal boundary close to a young star, high temperatures vaporize delicate volatiles. This leaves behind dense, rocky worlds like early Earth, which must rely on secondary impacts from water-rich asteroids and comets to deliver their surface oceans. Beyond the snow line, however, water remains continuously solid. It accretes into massive ice giants, icy moons, and volatile-rich comets that stock outer planetary systems with immense, unimaginable reservoirs of water ice. Spectroscopic analyses of exoplanetary atmospheres have identified water vapor drifting through hundreds of distant star systems. Worlds designated as Hycean planets, large exoplanets possessing hydrogen-rich atmospheres and vast planet-wide oceans hundreds of miles deep, demonstrate that liquid water environments may actually be among the most common planetary habitats in the entire Milky Way galaxy. Why is water the undisputed medium of life across the universe? Its chemical versatility stems directly from its unique molecular structure. The bent geometry of the water molecule creates a strong electric dipole moment. This polarity enables water to perform several critical biological and physical functions that no other solvent in the universe can match. Its high dielectric constant attenuates electrostatic attraction between ions, allowing it to effortlessly dissolve salts, minerals, and complex polar organic molecules required for metabolism. Its hydrophobic effect forces non-polar molecules to aggregate together, which spontaneously drives the folding of complex proteins and the self-assembly of living cell membranes. Furthermore, water exhibits a unique density anomaly, where solid ice is actually less dense than liquid water. Because ice floats rather than sinks, it creates a protective insulating layer over underlying liquid oceans, preventing deep marine environments from freezing solid from the bottom up. Water also possesses a remarkably broad liquid temperature range, combined with a high latent heat of vaporization and fusion. This thermal inertia stabilizes planetary surface temperatures across wide orbital variations, protecting emerging life from volatile temperature swings. Because of these unique thermodynamic and chemical attributes, astrobiologists searching for biosignatures across the cosmos follow a simple, fundamental directive: follow the water. Where liquid water interacts with a rocky core and an active energy source, the chemical foundation for life is invariably present. Every single drop of water on Earth today is an ancient survivor of cosmic history. The hydrogen atoms in your blood plasma were born in the first 3 minutes following the Big Bang during primordial nucleosynthesis. The oxygen atoms were forged in the fiery nuclear furnaces of massive stars that exploded eons before our solar system condensed from interstellar debris. When you drink a glass of water, you are literally consuming the cosmos itself. The liquid that carved the Grand Canyon, filled the dark abyss of the Mariana Trench, sustained the dinosaurs, and carried human navigators across vast oceans is the exact same fluid circulating through your body right now. Water is the ultimate eternal connector. It binds the birth of stars to the geology of planets, the chemistry of oceans to the architecture of microscopic cells, and the deep past of the universe to the present moment of your own conscious breath. The journey begins with Big Bang nucleosynthesis forging hydrogen, while stellar nucleosynthesis creates oxygen. These elements unite in interstellar space to form water molecules, which are delivered to young planets through asteroid impacts. Once deposited, these molecules fill surface oceans, circulate through atmospheric clouds, and pass through subterranean aquifers, eventually becoming part of living organisms and conscious minds. As the sun gradually warms our world over geological time, surface evaporation will accelerate, forcing water to retreat down into deep crustal aquifers and polar subsurface brines. Yet, even as surface seas disappear on Earth, distant exoplanetary systems across the galaxy will continue to harbor vast ocean worlds and icy subsurface moons, keeping the cosmic presence of liquid water vibrant and alive. Consider the sheer scale of the global hydrological cycle that has sustained our world for over 4 billion years. Every year, hundreds of thousands of cubic kilometers of seawater evaporate into the atmosphere, driven upward by solar energy. This invisible vapor rises into the atmosphere, cools as it ascends, and condenses around microscopic dust particles to form clouds. Driven by atmospheric winds, these clouds travel across thousands of miles of open sky before releasing their moisture as rain, snow, or sleet. When rain falls upon the land, it begins a complex journey back to the sea. Some of it runs off directly into streams and major river systems, carving through rock and transporting essential mineral nutrients into coastal estuaries. Some of it infiltrates deep into the soil, replenishing subterranean aquifers that store vast reserves of fresh water beneath the continents. Trees and plants draw this groundwater up through their roots, drawing minerals into their tissues and transpiring water vapor back into the sky through microscopic pores in their leaves. This ceaseless circulation of water is the planetary engine that drives global climate, shapes continental geology, and fuels the biosphere. Without the continuous distillation of water through evaporation and precipitation, the land masses of Earth would be sterile, mineral wastes. Water is the dynamic medium that translates thermal energy into weather, weather into erosion, erosion into soil, and soil into life. Within the biological realm, water functions as the master solvent that enables complex chemistry. Inside every living cell, water provides the medium through which nutrients, enzymes, and metabolic waste products move. It holds proteins in their functional three-dimensional shapes, enables nucleic acids to store and replicate genetic information, and participates directly in chemical reactions like photosynthesis and cellular respiration. In photosynthesis, plants use the energy of sunlight to split water molecules apart, extracting hydrogen to build organic sugars and releasing oxygen gas into the atmosphere as a byproduct. Every breath of oxygen you take today exists because ancient photosynthetic organisms learned to split water molecules billions of years ago. The air we breathe and the water we drink are fundamentally linked through the chemistry of life. In human biology, water regulates body temperature through evaporative cooling, cushions delicate tissues like the brain and spinal cord, lubricates joint surfaces, and transports essential nutrients and oxygen to trillions of specialized cells through blood plasma. Our bodies are constantly balancing water intake and output to maintain optimal fluid levels, osmotic pressure, and electrolyte concentration. When dehydration occurs, cellular function degrades rapidly, highlighting our absolute dependence on a continuous supply of this vital fluid. Beyond its physical and biological roles, water has shaped human culture, civilization, and history. The earliest human civilizations emerged along the fertile banks of major river systems: the Nile in Egypt, the Tigris and Euphrates in Mesopotamia, the Indus in South Asia, and the Yellow River in China. These ancient societies developed complex irrigation networks, flood control systems, and water storage infrastructure to harness river flows for agriculture, enabling population growth and the development of cities. Throughout history, oceans, seas, and navigable rivers have served as primary highways for exploration, trade, and cultural exchange. Maritime trade routes connected distant continents, allowing goods, technologies, and ideas to spread across the globe. Seaports developed into bustling centers of commerce and cultural interaction, driving economic growth and global integration. In modern times, access to clean, fresh water remains a critical factor for human health, economic development, and social stability. As human populations grow and climate patterns shift, managing water resources sustainably has become one of the most pressing challenges of the 21st century. Protecting freshwater ecosystems, improving water infrastructure, and developing efficient water management practices are essential for ensuring a secure future for humanity. The story of water is truly the story of everything that was, everything that is, and everything that will ever be. It is the silent architect of our world and the carrier of our biological destiny. As the long narrative comes to a close, we return to the simple, serene presence of the fluid around us. The oceans continue their quiet surge against distant shores. The deep aquifers flow slowly through ancient underground stone. The clouds drift softly across the blue expanse of the sky, dropping fresh rain upon the waiting earth. In this quiet moment, as you listen to the steady, rhythmic cadence of the rain outside, remember that you are not separate from this great planetary cycle. You are water that has learned to walk, to feel, to think, and to wonder. The long journey from the cold stars to the deep ocean and into the quiet pulse of your own heart is complete. The night is vast, peaceful, and still. If you found this video useful, don't forget to like, subscribe, and turn on notifications so you never miss our latest updates. If you have a question, an experience to share, or a topic you'd like us to cover next, leave a comment below. We'd love to hear from you. Thanks for watching, and we'll see you in the next video.